In this video, we're going to talk about 4 different important kinds of elements of an integral domain. So for the duration of this video, R is an integral domain. So as always, commutative with unity and no zero divisors. All right, here's the first definition. And you may have seen this one before because we've used it a couple of times, this word. An element U in R is called a unit of R if it has a multiplicative inverse in R. And that's it. That's the first definition. So any element of R, an integral domain, that has a multiplicative inverse is called a unit. And as you probably know by now, an integral domain could have lots of units or just a few units. So for example, in the ring of integers, that's an integral domain. The units are 1 because 1 has a multiplicative inverse. And are there any others? Yes, there's at least one more, -1. But that's actually a 0 is not a unit because 0 can never have a multiplicative inverse, and none of the other integers have multiplicative inverses in the ring of integers. All right, here's another example that's a little more entertaining. How about Z mod 5? In Z mod 5, the units are everything non-zero because we know that Z mod 5 is a field. So everything here has a multiplicative inverse. And in fact, we can keep track of who is whose inverse. 1 is its own inverse. 2 is the inverse of 3. 3 is the inverse of 2. And 4 is the inverse of itself. And in fact, in Z mod P, the units are everything non-zero. Just to give one more nice example, there's a ring called the Gaussian integers. The ring of Gaussian integers is the set of all a plus bi, so these are complex numbers, where a and b are integers. These are called the Gaussian integers. And in this ring, we still have units 1 and -1, but we have a couple of others as well, I and -I. But those are the only Gaussian integers that have multiplicative inverses. The way that you prove that fact, I'm not going to give a proof here, but the way that you prove it is by using something called the norm of a Gaussian integer. And the norm of a Gaussian integer is defined to be norm of a plus bi equals a squared plus b squared. And you can show that this is a multiplicative function on the Gaussian integers. In other words, if you take two Gaussian integers, take their norms and multiply them, you get the same as the norm of the product of those Gaussian integers. So that allows us to show that, first of all, the only way we can have a unit is if we have a norm of 1, and the only elements of Z bracket I that have a norm of 1 are these 4. Okay, so those are just a few examples. One fact that's good to know about units is that they form a group. The units of an integral domain R form a group under multiplication. And here's a quick little argument for that. First of all, we know that R always contains unity because it's an integral domain, and that element is a unit, since it is its own multiplicative inverse. All right, so we know that the set of units is non-empty. Now suppose U and V are units. We're going to show that this set is closed under multiplication. Then we know that U and V have multiplicative inverses. Call those U inverse and V inverse. So we also know that UV times U inverse V inverse, that is equal to UV, U inverse, V inverse, and because we're assuming we're in an integral domain, therefore multiplication is commutative, we can just reorder things and get this. And that's 1 times 1, which is equal to 1. So I realize when I write this, it probably looks like I'm saying 11. That's multiplication there. I was trying to avoid using the multiplication symbol, but there you go. Okay, so that means that UV is a unit because it has a multiplicative inverse. That inverse is right here. So UV is a unit. Okay, we also know if U is a unit, then its multiplicative inverse is a unit. First of all, we know that it has a multiplicative inverse because it is a unit, and then once we have that inverse, we can say this is also a unit, since we can say U inverse times U is the multiplicative identity. Okay, so we have a multiplicative inverse for U inverse, it's right here. And finally, we know that multiplication on the set of units is associative because multiplication is associative in R. It is associative. That associative property is inherited from R. All right, and so I think we've proven all of the conditions necessary for the set of units to be a group. We've proven closure under multiplication. We've proven that there is an identity. We've proven associativity. And we've proven that units have inverses also in the set of units. So there you go. So the set of units is a group under multiplication. Good to know. All right, what about the other definitions? So here's another definition. If A and B are elements of R is still an integral domain, then A and B are associates if there exists a unit U in R such that AU equals B. So in other words, two elements of an integral domain are associates if we can get from one to the other by multiplying by a unit. Okay, so here's an example. In the set of integers, 5 and negative 5, it's a 5 there, those are associates. Since 5 times negative 1 is a unit, is equal to 5. For that matter, we could also say 5 and 5 are associates, since 5 times 1 is equal to 5. Okay, so 5 and 5 are associates, 5 and negative 5 are associates, but you won't find any other associates of 5 in the ring of integers because 1 and negative 1 are the only units we have to multiply by. All right, what about in a field? In a field, any two non-zero elements, that is, are associates. Okay, why is that? Well, if A and B belong to F and are non-zero, then we know they're both units, so we can say A times A inverse B, that's equal to B. And I know that what I'm multiplying by here is a unit, since, first of all, I know A is a unit, therefore its multiplicative inverse has to be a unit. That's what we just proved. And B is a unit, and units are closed under multiplication, so A inverse B is a unit. So any two non-zero elements are associates. A slightly more entertaining example, in Z bracket I could take some complex number like 2 plus 3i and multiply that by something that I know is a unit. So how about I? By the way, we know that I is a unit because its multiplicative inverse is negative I. I didn't say that earlier, but should have. That product is going to be 2i plus negative 3 because those two i's multiply to negative 1, so 2i minus 3. Rewriting that in standard form, I get negative 3 plus 2i. So these two elements, 2 plus 3i and negative 3 plus 2i, these are associates. And there are other associates of those two Gaussian integers. I'm just showing you one of the pairs here. All right, so now let's move on to irreducibles and primes. So there's an interesting distinction between these two types of elements. And it's going to seem a little strange at first because it's going to seem like maybe the reverse of the way you learn things in grade school. But here's the first definition. An element x belonging to R, again an integral domain, is an irreducible, or sometimes we just say is irreducible, if x is not a unit and whenever x is written as a product AB for A and B and R, we have that A is a unit or B is a unit. Okay, so written in a little bit plainer language, what we mean is to say that x is irreducible means, first of all, x is a non-unit, and any factorization of x as a product of two things, as a product of two elements, involves a unit. Which is kind of like the definition of prime that you encountered in grade school. Now that definition may be different in a couple of ways, but probably one thing you remember learning is that, for example, 13 is a prime because the only way we can factor 13 is as 1 times 13 or 13 times 1. And in both of those factorizations, the number 13 occurs and the number 1 occurs. Now that's in the ring of integers, but in the ring of integers there is something else that we can do. We can also factor 13 as the product -1 times -13, or as -13 times -1. But in all of these cases, all of these involve a unit. So that's how we take our thinking about prime numbers and generalize that to an integral domain, is we say an element is irreducible, first of all, if it's a non-unit. So that would exclude things like 1, the integer 1, for example, from being irreducible. But then, in addition to being a non-unit, any factorization into two elements has to involve a unit. So that's the meaning of irreducible. Should seem a little bit like the way we define primes or prime numbers. But there's this other thing in ring theory, in the theory of integral domains, that is called a prime element. And the definition is actually a little bit different. An element P in R is a prime if P is a non-unit. Okay, so again, we require it not be a unit. And whenever A and B are elements of R such that P divides AB, we always have P divides A or P divides B. Okay, so that's a little bit different now. So we're saying that an element of an integral domain is prime if, first of all, it's a non-unit, and also it has this property that if that element divides a product of two elements of the integral domain, then it has to divide some one of the elements. Now this should look reminiscent of something. This should look familiar from when we talked about some of those lemmas in number theory. You might remember that we had a lemma, first of all, and this is a lemma about integers, not about general integral domains. But if A divides BC and the GCD of A and B is 1, then A divides C. And a corollary of that was that if P is a prime integer that is, and P divides BC, then P divides B or P divides C. And the reason that that was true when we were talking about the integers was if P doesn't divide B, then that's going to result in the GCD of those numbers being 1, which means we can use Euclid's lemma to say that P divides C. So in other words, prime integers behave in the way dictated by this definition. So a prime integer is a prime in the integral domain sense. But the definition of prime is more like what it means for an element to be irreducible. And what we're going to find in a subsequent video is that these two concepts are related, but they're not exactly the same. Stay tuned.